All right, welcome back, everybody. Today, we are starting a new chapter. Overall, just kind of first thought, egg drop, if and when I teach physics again, do it again. Any major changes that you think I should make to it? Materials. So that's always the weird one. I don't want to give anybody the ability to do it at home, because if you got a lot of money at home and a way to get to 3 bears, you have an unfair advantage in the process. I'm open to different materials. Yeah, I'm good with that. Sweet. All right, so today we get to start chapter 5, and I don't even remember the name of chapter 5, but we're going to figure it out right now. Chapter 5, we are taking a big leap, and that's not really true. That makes it sound scary. It's not. We are taking a small leap in a similar direction. So here we go. Over the next however many days this takes, I think there's 3 sections in here. So I don't know, week or 2. We are going to be looking at chapter 5. And within chapter 5, physicists, we are going to be looking at displacement and force a bit more. And I would suggest, if you would like to make this a little bit shorter, we do have a shorthand for displacement, right? Let me rephrase that. What's the shorthand for displacement? Yeah, delta x, change in x. So we have displacement and force, which I've been kind of fast and loose with this idea, but we're going to start doing this. I'm going to put that vector arrow back on in 2 dimensions. Now, every time we've talked about these things, it's always been in a single direction, or a pair if we're looking at the normal force. So typically, if something falls, its direction's down, right? And opposition, whether it's normal or whatever, is upward. And that's just 1 dimension, even though it's up and down. Okay, realistically, how often is it that when we're dealing with stuff, I just drop it straight down? Is that really common? Maybe, it depends on the situation. I'd say much more common when you're looking at falling objects, whether we're dropping them ourselves or we're studying something that's moving, that path is much more likely, right? Nothing, not a straight line, typically it's some sort of curve. So we're now adding a 2nd dimension to these things. Okay. Our first section, we get to focus on these vectors, and we've hit them at least a little bit, but we'll jump in with vectors, and we'll see. Can you guys see that red okay? Anybody struggle to see it? Is a better way to ask that question. Okay. In 5.1, our focus is going to be on vectors. Now, remind me, what's a vector? And I'll try this a different way. 20 seconds, talk with your neighbors. I'm going to call in 1 random person. I need you to tell me what a vector is. I'm not a crab. This is me telling you to talk. Man, I don't have a calculator of any sort right now. I don't know how I messed it the first time. Yeah, you're right. Wait, my other one's right there too. Odd. All right, and the winner is number 1. I don't know who's number 1 in here. Hey, number 1, what you got? So yeah, 100%. So this is a quantity. It's just a number. It's a representation, a way to talk about it. But it only has 2 things. It has a direction, which is typically going to be some angle, which we'll call theta, T-H-E-T-A. And then it's also going to have a size or a magnitude. Now, this can be a weird idea when we're thinking about it, because if I think about the size of velocity, that's a weird way to word it, right? But if I said, how big is a velocity, does that question make more sense? Like, maybe to some of you, I saw yes and no. To me, it does. The size is just the overall, like, it'd be the length of our vectors, we're talking about it. But whatever the quantity is, the size of your force, the size of your velocity, the rate, like, I'm trying to think of another way. Anybody have an alternative to talk about size or magnitude? Say it again. So I wouldn't say just mass. We'll get practice with it if the size also didn't feel good here. Now, looking at it, they're directed line segments is really what they are. So they're just a piece of a line that has a length and a direction. Cool. We're going to make the jump, and I don't like the red color. I struggle to see it. So our first main topic here is we're going to jump forward. We are looking at vectors in 2 dimensions. And 2D is just the shorthand for 2 dimensions. Now, before, just as a quick kind of review, I'm going to draw 2 vectors on the board. And I'm just going to name them A and B as vectors. And we'll just make this a little recall right off the bat. If I have vector A, which if I want to indicate that this really is a vector, what should I do to this? What mark do I put above it? It's like the half arrow. And A might have been a bad choice because we use acceleration a lot, but I'm going to stick with it. A with this mark tells me it's a vector. So let's say we have vector A that looks like this, and it's doing this thing. And I want to add to this vector B, which same thing, it's just kind of ugly. And let's say it's this length. And I'm going to try to make it as best I can, also horizontal. If I want to do A plus B, how do I do it? Tip to tail. Now, if I look at how this goes, vector A right here, and I'm just going to put a length on. Let's say that this is 5 whatevers and 3 for our magnitudes. If I wanted to add these the old way, I go, here's vector A, and I've drawn it, and I'll go ahead and label it. And where do I put vector B now? I start vector B right here at the tip, and it happens to also go this way. If this were vector B, and I have them both written, what do I call the answer when I add these? Because I get a new single vector, I think, that I could represent from here to here. The resultant. Nice job. This is my resultant R. Cool. Now, I'm going to switch to capitals here in a minute. Lowercase is much more common in math, but we're going to use capitals starting here shortly so it aligns better with your book. Tip to tail. Can you tell me the magnitude of the length of vector R right now? 8. 5 and 3 indeed makes 8. Okay. That's what we've seen of vectors so far. All of this look familiar to you guys? Cool. Now, here's where we're going to make this little change. As we look at this, these vectors are only moving left and right. And in fact, they're only moving right currently, but I can think of a left vector in that same straight line. There's nothing crazy about it. I want everybody to stand up real quick. And then you're going to have to find a space to take a step somewhere. Let's go to the hallway. Let's do that real quick. I'm going to pause it. All right, I'm going to talk loudly in here before we go. Instead of just looking at this, which is where we started in initially earlier in the year when we were talking about vectors, I want to actually extend it. Let's think in 2 dimensions. Or, because it sounds cooler, let's add a dimension. Now, the bulk of mathematics that you guys ever deal with is in 1 or 2 dimensions. You'll get a little bit of the 3rd dimension showing up in a Geometry or Algebra 2 class. You guys remember solving systems of equations? Like substitution, elimination, all that stuff? Do you remember solving, instead of 2 equations and 2 variables, 3 equations and 3 variables? A 3x3 system, you might have used matrices and Cramer's rule and all that good stuff. You're doing math in 3 dimensions. You're looking at big flat surfaces and where they intersect in 3 dimensions. Can you imagine, not graphically and not conceptually really, but can you imagine an equation in 4 variables? And to solve a system in 4 variables, you need how many equations typically? For 2 variables, we need 2 equations. For 3 variables, we need 3 equations. For 4 variables, you just need 4 equations, right? Now, looking at it, if you guys agree that we can have ax plus by plus cz plus maybe, I don't know, dw or something with that, a 4th variable, we can now do 4-dimensional math. We can do 5 or 6 or 7, doesn't matter. Our 3-dimensional world is pretty common, but we can add more without any issue. When we add a dimension to our vector stuff, there's 2 possible ways that this is going to work out. The first of these are as nice as they get. We're going to talk about perpendicular vectors. Okay, so I'm going to use 2 vectors, and we're just going to look at this, and my guess is you guys are going to be okay here. So we'll do a quick EG, bless you, rather than looking at things, and I'm going to switch to my capital letters. Let's say that we just agree that up is north, down is south, west and east, okay? Let's say I walk 5 meters north from my starting point. So notice 5 meters and north, I've given us a displacement. Cool. We get to the end and I turn toward the east, let's say for 4 meters. Nope, I lied. We're going to make this a little bit bigger. Let's make it 9. Okay. If I look at these, do I have 2 vectors right now? I'm going to name this one just so we can get consistent with it. I'm going to call this vector A, and I'll call this one vector B. If one was north and one was east, we get this angle, right? It's a nice, lovely right angle. If I wanted to draw my resultant, just like we did here, where notice it's just I start at the tail of the first vector and I end at the tip of the second. Could you draw your resultant here? Do it. I'm going to come around and look at your pages. Draw your resultant for this specific situation. Okay, so as I'm looking around at stuff, tip to tail still works. Notice I just added this one here. My resultant starts at A, and I'm going to try to use a dashed line here in a second, and it ends here. Okay, too big of an eraser. As we look at this, it is really common to call this vector C, but I'm going to hold off. I'm going to call this vector R, because why? It's my resultant. Cool. Now, looking at this, could you find the length of vector R? How? We use the Pythagorean theorem. So, just as a quick reminder, I'm going to teach some notation real quick, and you guys have to let me know if you love it or hate it. It's formal math notation. This is what we use for vector, right? So I'm going to throw this in underneath. Up to you whether or not we use this. Vector A has a length of 5 meters, right? A magnitude, a length, whatever you want to call it. This is really common in mathematics, what we use to represent the magnitude of a vector. It looks like absolute value, it's 2 vertical bars. If we're only talking about a vector, this is really nice because typically if you think back to geometry, and we'll say if it's gray, put the pencil away, just like we have been. In geometry, if we wanted to talk about these, we don't really just call this whole vector A, right? Normally in a geometry class, you'll call this point A, point B, and point C. And then you have a nice way to talk about, oh, the length of A to B can be written as AB. But if we don't need the endpoints, we need a new notation to make it really clear that we're talking about the length. Would you guys agree with that statement? Thoughts on using the actual true symbol for magnitude? Sweet, we're good with it. Let's use it. Double vertical bars is not absolute value. It is the magnitude of a vector. So I want you guys to add it. We'll commit to this. Is the magnitude of vector A. And then we're going to use it in a few minutes. So I'm just going to go ahead and write it right now. I want you to know, super redundant. You do not need to write the word vector in front of this. The second that I put that A with that arrow above it, it's read as vector A. Like we understand it's a vector. That says vector, vector A. It's redundant. Okay. When we talk about this, other little pieces, we use commonly, we'll start anyway. What's the most common angle variable that we use? Greek letter. Theta. And I'm going to say in degrees, in this class specifically in degrees. I can spell degrees for angles. So theta is really formally, it's this circle with the dash through it. When I draw it though, I do a circle here, then I just loop back around and I just make it horizontal. So that's what my theta is going to look like. And actually it'll look like this because I draw it faster. Cool. All right. So we'll use this stuff here. I want you guys, we've already spoke a little bit about it. I want you in this specific example to find this. And what did I just ask you to find? Love it. The magnitude of the resultant, or the vector r, whatever you want to word it. Okay, you guys, Pythagorean. Whoa, I was trying to make it like a nice adjective verb thingy. Pythagorean it up.
That's what it is.
There's a sign out sheet back there, totally, and then there's a digital clock in the window to your right. What's up? Yep, R squared in this situation, but yeah. Yep, 100%. Now, you'll notice the notation does get cumbersome, right? It gets kind of ugly. I will be really consistent with mine. If you just write a squared plus b squared equals r squared without the vertical bars, am I going to destroy you? No, but make sure you know that you're talking magnitude stuff. Can I just do one line of work? All right, what's 5 squared? 25, and what's 9 squared? What's 81 plus 20? So, and 5 more gets me to 106. So I, at this point, think that I'll probably show 2 lines. I know that r is the square root of 106. And then, what's the unit on it still? So careful. I heard meters squared, I think. Is that what you said, Fern? Okay. It would be meters squared, right? Because we take these things, we square it. But as soon as we take the square root, it just turns into meters, yeah? Okay. Now, decision time. And you're going to see my opinion change drastically between now and 2 hours from now, just so you guys are aware. In math class, I love this answer. There's better ways that we could do it, because I would actually like to try to break this down if I can. What is it? 2 times 53, and 53 feels pretty prime to me. Is 53 a prime number? Feels prime. Okay, this is a good answer in a pre-calc or math class. If you tell somebody in physics, yeah, go ahead, walk root 106 meters this direction, you're going to look at them like they're dumb, right? Because that's a silly way to say it. What should we do in this class? Change it how? So this is a little bit bigger than 10. I just don't know the decimal. 10.29. That is larger than I thought it was. 10.29 meters. Okay. This situation is so incredibly nice. Perpendicular stuff, piece of cake. But it's not usually perpendicular. Like, most of the time, this doesn't happen. So this is going to feel strange, I think. But before we get here, we have perpendicular. And I'm going to make one more comment. And then we're going to have to nest some stuff beneath here just to do a quick review game. Like game, I mean, it's going to be fun. We're going to talk about trig. Not really a game. Okay. Before moving on, questions about right angles? Feels okay? Feels terrible? All right. Sweet. Love the feedback. Okay. What if they're not right angles? And I'm just going to say not perpendicular. So, for example, if we're looking at something, I don't know, like this. I want to go, and I'm going to write a few words here, okay? We're going to say walk 5 meters south. Turn, and then we're going to check just some understanding here. If I write this, so we're walking south, and I want to turn, let's say, S 35 degrees W. Anybody know what that says? Because I don't recall if we talked about it here. Say it again. Can you say it one more time, just like twice as loud? I'm sorry. So if I said right now, draw me that direction on your page, could you? So like there's maybe some little issues. What shows up first in this? So I'm gonna like just put it in parentheses here. Actually, I'll do it above because I have room. This thing is read as 35 degrees west of what? South. Now, the way, I don't know why that's capital. Are these capitalized directions? I don't know. We're going to learn real quick. All right, so it is not capitalized. We'll fix that. All right, how far do they walk? Let's do 20 meters. And then, just quick, easy question. What is displacement? And we may have to leave this hanging for a minute. All right. So, first thing, would a picture help? 100% yes. Do me a favor. I want you to try to draw it. Or we can draw it together, but I think that we should draw it together. All right, let's start. Real quickly, by default, unless otherwise stated, we're just going to agree up is north, down is south. Cool. What direction do I walk first? All right, so check it out. Here I am, and I got to think this out. We're turning west, so I'm actually going to move this over 1 square. Check it out. Here's vector. I don't know. What do you want to name it? Sure. Oh, I would be wary of W because west. I'm okay with A. V is really common, and you'll see it in pre-calc later this year. V is really common. V, U, W are typically what we start with, but it doesn't matter. We'll use F really commonly as a vector in here. Okay, I've walked south for 5 meters. Love it. We'll just write 5 meters right here. And then I turn, right? Now, here's the weird part about it. You can sketch this, and I typically do. I would extend past, but make very clear that it's a dashed line. When we're looking at bearings, which is what this is, this would be an example of a nautical bearing. It is not the same as like airplane bearings because they measure differently. But I'm now asked to turn, and I start at south. That's what this tells me. Start at south and then go 35 degrees to the west. So I'm going to change color. I'm going to have vector B, or the second part, that starts here. We're still doing tip to tail. And then I have the ability, remember, I can move my piece here, and it's longer. So it's not going to be like perfectly to scale. Right now, I'm going due south. Do you guys agree? Okay, which means 35 degrees to the west. Should I move to the left or to the right? Look at a map. The West Coast is on which side of the U.S.? The left. Okay, so I have a choice here, though. I think that this looks pretty close to that angle, but one could argue that they think this looks pretty close to that angle. It is going to be this one, just so you know, like I'm not even gonna like play the game with it. Here is my second trip, and it's not to scale, but we'll call this vector B, and that's 20 meters of length, or magnitude. Where on earth is my 35-degree angle? So right where? So that's a good thought. That's what I'm expecting. Good answer. Wrong answer, but good answer. This is really common for what people want to say that angle is. We will find that angle. We'll be able to. But check it out. We turn 35 degrees west of south, right? Here's my 35-degree angle. I'm going to call it theta for now. Because that's exactly my 35 degrees west from south. If I wanted the resultant now, and I try to draw this in, and I don't remember what color I used for the resultant, yellow up there. I'm just going to be inconsistent with that. I start at A, and I end at B. This is my resultant R. Everybody's still on board currently. Okay. This might be futile. We might not get anything out of this, but I'm just going to do a quick check to see how much trig stuff you remember. I'm going to give you about 45 seconds to discuss with your neighbors. Can you find me the length of R? 45 seconds, talk it out. Throwing a little shade. I'm expecting no, but I would love to be surprised. So check this out. I'm going to make a copy of this, and I don't know if I can blow it up or not. I'm just going to sketch another one. You guys don't have to draw this. If we think about just a triangle, here's our triangle. And Sean, I just heard you say something. I know that's 5. I know that's 20. And here's my 35. What is this whole angle right here? The whole way through? 180. And if we subtract the 35 from down here, like if we just take it away, we get this angle, right? Just the inside. So 180 minus 35, I believe, is 145, which, Sean, that's what you said, right? Cool. So I now know a 145-degree angle right there. It makes me know a little bit more about the triangle, but does anybody know how to solve a 145-degree angle triangle? Ooh, I like that we're hearing stuff. Why tangent? So I like that idea. Here's my one little concern. You're kind of right. SOHCAHTOA has been used before, right? Does everybody recognize that language? Can you spell it for me? Good. Lots of confidence in that. Okay. Here's the deal. Right now, we don't have enough to solve this. We're going to let this just leave it blank for the time being, okay? We are going to sneak in a really quick trig review for like the next 10 minutes or 5 minutes. We'll start it, 5 to 10 minutes, and I'm going to give you guys the rest of the time to work on things as discussed at the beginning of class. Okay, so right off the bat, my favorite thing about teaching geometry is when we get to trig. I teach SOHCAHTOA, and I make up, because it's the way my geometry teacher did it, I make a big elaborate story about a famous Lakota war chief, because that's where I'm from. My teacher was a Lakota guy, and he told us this big long story, like took 25 minutes of our time, and it was a lie. None of it was true, and I tell the same story to everybody, and it's so cool to like have everybody engaged in this story and then tell them it's all nonsense and made up. We're going to come back to this. Let's start here, and it's just going to fit in ugly. Trig review. Now I'm going to write actually trigonometry, but you do not have to. All right, so metry is a study of the measures. That's what it means. When you see metry, that's all that words. Metric is a measurement of something. A trigon, I talked about it in the hallway. What's a trigon? Triangle. Trigonometry is literally just the study of the measure of triangles. So, looking at this, real quickly, most important thing, SOHCAHTOA does not directly apply here, because we require to use like true SOHCAHTOA really nice triangles. When I talk about really nice triangles, that's what? 90 degrees. So check it out. 4 right triangles. We can use and I'm going to write this out, and we're going to have a bit of writing. If I'm going way too slow, please tell me. So, S-O-H, Ka, C-A-H, Toa, T-O-A. Now, I write them capital like this to really stress the importance. So gets used to represent something. Do you guys remember what? Yeah, say it again. So I know that this one links up with sine. How about ka, the C? Cosine. And how about the T? Tangent. Now, there is a link between tangent lines that we've discussed when we're talking about how the rate of change of something is, or with your derivatives. There's a link between these, but it's not as nice as you would want it to be. These are all ratios. These are all just fractions. These are functions. There's a lot of ways we can talk about them. For any of these, we have shorthands though, because I doubt you guys regularly write cosine like this. What's the shorthand for sine? Look at your calculator, you'll see it. S-I-N. Just heads up, drives me crazy. It's not sin. It's sine. Okay. So we're going to write some stuff, and we're just going to talk about like the basic. If you want to take the sine of something, you are taking the sine of an angle is what's going to happen. So just to get some math language, if we have an angle theta that we're looking from, sine of theta, this is a function, and then you can write it if you want. You're going to hear me refer to this as the argument over and over and over. The argument of this sine right here is theta right now. Okay, How do I remember what sine is equal to using SOHCAHTOA? Say it again. No, I think you're right. Just say it again. Something over hypotenuse. Opposite side. That's our O. So we're going to say that sine of theta is opposite over, the H stands for hypotenuse. I'm going to shorthand these, op and hype. If you want to write the full word, please do. Okay. The sine of theta is equal to the opposite side length over the hypotenuse. This all ring a bell. Okay. What's the shorthand for cosine? And I'm going to change colors and is going to hate it. Maybe I don't have to. What are the 3 letters I'm going to use to represent cosine? So the cosine of my argument, and check this out, this might annoy you guys. Whether you put the argument in parentheses or not, doesn't matter. You disagree with me totally, that's okay. There will be a point, I think you disagree, I can't tell. So there will come a point where it might matter, but you can always not use it, except one situation. What's cosine? Cos theta is, A stands for the adjacent side, not an adjective, the adjacent side over the hypotenuse. Cool. So, what's the argument of this cosine? Theta. Whether there's parentheses there or not, the argument is theta right now. Okay, shorthand for tangent. Tan theta. And then notice we can put the parentheses there or not, doesn't matter. How do you find tangent? The opposite side length over the adjacent side length. Okay, all of this is, I think, just geometry, just a geometry idea. Can't stress it enough. SOHCAHTOA works for which sort of triangle? For right triangles. Okay, last little piece, just so we can talk about it. You do not need to write this, okay? We're not going to add any more trig stuff, but I do want to talk about these parentheses because it can be odd. If we're looking at it, if I write this, sine of theta plus 1, what's the argument right now? Theta plus 1. I'm taking the sine of that angle, whatever theta plus 1 is. And it'll either be an angle in degrees or radians. I don't think you guys saw gradients last year, did you? I doubt you've seen gradients. You've seen radians, I think. Maybe you did. I don't know. Probably not. Okay. How about if I do this? Is this the same thing? This is the one situation where it gets weird. What's the argument of that sign? Just theta. If you want to have your argument include more, you need to include it. This is where the implied parentheses are. Always just connected. Okay, last one. What's the argument here? 2 theta, same thing, but I would change the language. 2 theta is the argument, absolutely. Cool. All right. How much of the unit circle do you remember? You think you got a lot of it? Yeah. Okay. Can you guys count up and down from 3? You can have the whole circle. Guaranteed. We don't use radians in here. We're going to pause here. Is this too slow for trig stuff? Just a heads up. Like, should I speed it up for tomorrow? Okay. Cool. You guys get 11 minutes to work on reflections or lab stuff. Angel, I'll print you a new one here in just a second. Cool. No new homework tonight. When's your lab due? Tomorrow at the start of class. I need your lab.